It's a question, isn't there? A profound and deeply human question that whispers at the edge of our thoughts, particularly in those quiet, reflective moments. It's a question that has fueled countless stories, dreams, and perhaps a few sleepless nights. What if he could step outside the relentless forward march of time? What if he could visit the past? And not just in memory as a fleeting ghost of what was, but to truly be there, to feel the air on your skin, to perceive the world as it once was. The classic thought experiment, the one that always comes up, is a rather violent one, I must admit. It's the grandfather paradox. Could you go back and, shall we say, prevent your own grandfather from meeting your grandmother? If you did, then your father or your mother would never have been born. And if they were never born, well, then neither were you. And if you were never born, who went back to commit the deed in the first place? It's a tangle, a logical knot that seems to slam the door on the past, bolting it shut forever. For decades, probably every physicist alive would have nodded in agreement. Time travel to the past, impossible, a fiction, a paradox. Just a quarter of a century ago, this sentiment was the bedrock of scientific consensus. Consider this thought from the 1970s. From a respected physicist writing in a scholarly journal. He imagines traveling back in time to his own 5th birthday. He perceives the children around the table, a younger version of himself, blissfully unaware of the temporal voyager in his own future. And he concludes that if he truly went back, then all trace of the intervening years, both inside and outside of him, must be gone. He argues that the party would be indistinguishable from the original one. In fact, it is the original one. And so, he declares, there are no consequences to time travel. A statement that it can or cannot happen is, in his logic, meaningless. He dismisses the idea of taking a present mind back to past events as pure fiction. And up until very recently, even the most imaginative, the most speculative physicist would have shared this deep-seated skepticism. Time machines and journeys into yesterday were the stuff of science fiction, and even the writers didn't truly believe it was anything more than a wonderful narrative device. They wrote these stories because we, the readers, are utterly captivated by the idea, but it was understood to be fantasy. This was in stark contrast to, say, stories about space travel. Getting to the moon or Mars or even the nearest star was perceived as a monumental engineering challenge, to be sure, but it didn't seem to violate any fundamental laws of nature. But traveling through time, no, that was a fairy tale. But something has shifted. The universe, as we have come to understand it, is starting to feel stranger and more magnificent than even the wildest pulp fiction stories of the 1930s. Once, the idea of a computer brain was a fantasy. Now, they are in our pockets, connecting us in a global web of information. Once, trips into space were derided as escapist nonsense. Now, orbital flights are so routine they barely make the news. And once, talk of time travel was a step too far even for the most outlandish fiction, but now, the theory of time machines is discussed in the pages of the world's most important physics journals in articles penned by some of the most brilliant minds on the planet. Physics, it seems, is arriving at an astonishing conclusion. The idea of traveling to the past may not, in fact, violate any of the known laws of physics. Now, let me be absolutely clear. Nobody has the faintest idea how to build a time machine from spare parts in their garden shed. But it seems that it might just be possible, with a technology so advanced it would appear as magic to us. Technology is the key word here, not science. The science, the deep foundational principles of our universe as we currently understand them, seems to permit it. But there are rules. Oh yes. There are profound and beautiful rules, dictated by the very fabric of reality. And it's those rules that transform the conversation from mere fantasy into the realm of possibility. It used to be that you could simply invent your own rules for time travel. Who could tell you that you were wrong? But since the late 1980s, physicists have uncovered so much of the real science of time travel that the made-up rules of yesterday no longer suffice. And, as we delve deeper, you'll begin to perceive the constraints that science imposes on an unbridled imagination. But you'll also sense that these constraints, these rules, aren't really so difficult to live with. They boil down to two central, majestic ideas. Firstly, if our universe follows a single, consistent timeline, then any events that form a closed loop in time must be self-consistent. You can't have a time traveler changing the past, although they can affect the past. And there is a universe of difference between those two words. Secondly, if a story truly depends on changing the past, then it must invoke the idea of multiple timelines, of splitting universes. Rather than limiting us, these two great principles should encourage us to think more carefully, more deeply, about the nature of time itself. The theory we have for time travel, the only scientific theory we've got, is Einstein's general theory of relativity. It is his theory of gravity, and as we'll discover, it is this very theory that seems to open the door to the past. This isn't just about telling a good story, it's about grounding that story in something real, something that respects the magnificent logic of the cosmos. Think of the ultimate male fantasy, as one author imagined it. An old man, the inventor of mind travel, journeys back into his own younger mind to be with the girl he let go in his youth. And at the end of the story, we learn that she, as an old woman, has traveled back to her mind on that very same day to be with him. There's no science in that story, not really, but who could deny its tremendous emotional power, its connection to a fundamental part of the human condition, the longing to revisit our choices? But our journey is a different one. It is a journey into the physics of what might be. A time machine. A machine built to navigate the fourth dimension. The very idea invites skepticism. I remember a letter written by a 17-year-old and published in a 1931 issue of Astounding Stories. He wrote, "There is only one kind of science fiction story that I dislike, and that is the so-called time traveling. It doesn't seem logical to me. For example, supposing a man had a grudge against his grandfather who is now dead. He could hop in his machine and go back to the year that his grandfather was a young man and murder him, and if he did this, how could the revenger be born? I think the whole thing is the bunk." That very same skepticism echoes down the decades. The modern writer Orson Scott Card called time travel an impossibility, a magic trick for writers. And as a storyteller, what you want from your audience is excitement, tension, and eagerness to turn the page, not raised eyebrows and a dismissal of your entire premise. So, while we don't want to turn our exploration into a sleep-inducing doctoral dissertation in physics, we do need to provide some rationale, some reason for what every scientist and every storyteller hopes for, a willing, temporary suspension of disbelief. So, if the fantasies were so vivid, what happened when the cold, hard light of 20th century physics was shone upon them? Did it extinguish the dream? Or did it, unexpectedly, give it a foundation in reality? The early pulp magazines, those wonderful, brightly colored gateways to other worlds, were a battleground of ideas about time. Their pages, printed on cheap wood pulp paper that gave them a distinctive smell, were filled with time travel tales, often filled with what we might now call fiction language, flowery, improbable dialogue, and, more importantly, science that took, let's say, poetic license with the facts. Hugo Gernsback, the editor of Amazing Stories, wrote in 1926 that authors often disregard true scientific facts to make a plot seem probable. I don't believe any good science fiction editor today would allow that. Readers are more sophisticated. They know that a light year is a measure of distance, not time, and so the stories have had to evolve. But the core questions, the deep philosophical puzzles, were being debated right there, in the letters pages of these magazines, long before they were staples of academic journals. This was a public conversation happening in real time. Time machines and time travel are radical topics that demand a skeptical reaction. Even if physics should one day place them on firm experimental ground, I think many people will persist in thinking of them as fantasy. In much the same way that a physicist who understands the intricate dance of light and water droplets still stands in awe at the appearance of a rainbow. The intellectual understanding doesn't diminish the wonder. Critics have long lined up to dismiss the notion. Kingsley Amis wrote in 1960 that time travel is inconceivable. Groff Conklin, a respected anthologist, wrote in 1953 that just as mad scientists in reality were once found inventing perpetual motion machines in science fiction, the lunatic fringe was trying to perfect time travel mechanisms. And who could honestly say they weren't correct? Could there be a bigger fantasy than going back in time and having another try at putting our muddled lives straight? The emotional hook is powerful. An editor of Thrilling Wonder Stories knew it when he hyped an upcoming story in 1950 with these words: "What's the biggest mistake you ever made? Don't worry about it. It's simple. Just look up at that old time clock on the wall and turn it back to the moment just preceding your terrible blunder. Then make your corrections. You may be starting a new chain of error, but why fret? You can go back in time again." This idea, the fantasy of redoing our lives, is potent. But it's crucial to distinguish this from a scientific exploration. There are endless fantasy mechanisms for time travel. Willpower, as in the romantic film Somewhere in Time, freezing, a classic trope from The Door into Summer. Even trauma, a knock on the head, as in Mark Twain's A Connecticut Yankee in King Arthur's Court. These are wonderful literary devices, but they are not our concern here. Our concern is with machines based on the principles of Einstein's general theory of relativity. Even within the realm of scientific explanations, the early pulp stories were a wild west of ideas. There was the Panchronicon, a machine that swung on a rope tethered to the North Pole, traveling through time by cutting the meridians faster than the sun. It raised paradoxes, changing the past, meeting yourself, but its mechanism was pure fantasy. There was even a strange poetic essay in a French literary journal in 1899 that described a time machine based on an analogy with a gyroscope, an idea that a well-known British physicist of the time apparently took seriously enough to write to a colleague about. These are fascinating artifacts of our imaginative history, but they aren't physics. The real, robust discussion began in the pages of Hugo Gernsback's Amazing Stories, which reprinted H.G. Wells's masterpiece, The Time Machine. This sparked a flurry of letters from readers. One, from July 1927, asked, "How could one travel to the future in a machine when the beings of the future have not yet materialized?" It's a brilliant question, and one we will answer. But a more interesting letter came from a reader identified only by the initials, TJD. He imagined an inventor traveling back to his own school graduation in the year 1900. "Will there be another 'He's on the stage'?" he asks. Of course, because he did graduate. Should he go up and shake hands with this alter ego? But then he pulls back. No, he can't go up and shake hands with himself because this strange other he did not appear suddenly and congratulate the graduate. He gets tangled in the logic of it all. What if the inventor decides to shoot his former self? He couldn't do it because if he did, the inventor would have been cut off before he began to invent, and he would never have gotten around to making the voyage. Help, help, I'm on a vicious merry-go-round. This letter captured all the classic puzzles, and it provoked a fierce debate among the magazine's readers. A story was published about a scientist who transports an entire ship 14,000 years back in time to hover over lost Atlantis. A reader wrote in, sharply criticizing a flaw in its logic. The Atlanteans in the story observed the time travelers. But, the reader asserted, the time travelers must have been invisible. Why? Now, one of the Atlanteans lived his life thousands of years ago and died. Now, back we come in time when A is again living his life. Lo and behold, this time A sees before he dies a strange phenomenon in the sky. And yet these people are necessarily observing him during his one and only lifetime, wherein he certainly could not have observed them. Gernsback, the editor, agreed. He concluded that the inhabitants of Atlantis would probably not have seen the travelers in time. This question of participation versus observation, of being an invisible ghost or a tangible actor in the past, became a central theme. In 1929, Gernsback published a story called The Time Oscillator, and with it, a direct challenge to his readers: can a time traveler, going back in time, partake in the life of that time and mingle in with its people, or must he remain a spectator who merely looks on but is powerless to do more? He laid out the grandfather paradox as the central problem. calling the idea of a traveler freely participating in the past an absurdity. The letters poured in. But one, from a San Francisco high school student named Jim Nicholson in 1931, was extraordinary. It laid out, with astonishing clarity, the plots of several classic time travel tales that had yet to be written. He proposed 4 thought experiments. First, the causal loop of the uninvented invention. A man takes a time machine and travels into the future from where he sends it, to the past so that he may find it and travel into the future and send it back to himself again. Hence, the time machine was never invented, but from whence did the time machine come? Second, the paradox of foreknowledge. A man travels a few years into the future and sees himself killed in some unpleasant manner. So, after returning to his correct time, he commits suicide in order to avert death in the more terrible way he was destined to. Third, the information loop. Travel into the future, find out how some ingenious invention of time worked, return to your right time, build a machine, similar to the one you had recently learned the workings of. Then, who really did invent the concerned thing? And finally, the ultimate biological paradox. What if a man were to travel back a few years and marry his mother, thereby resulting in his being his own father's? Kernsback's reply was favorable, but he concluded that Nicholson was right, that partaking in the past could disturb the normal course of events. But as we will see, contrary to Gernsback's view, while Nicholson's questions are ingenious, his conclusions and Gernsback's are not necessarily logical. And so, this brings us to the threshold of modern physics. It's time to leave behind the wonderful speculations of the pulp magazines and step into the world of Einstein, of space-time, and of a universe far stranger than we ever imagined. Time is a mysterious concept, a mystery that seems to deepen the more we contemplate it. The ancients were as perplexed as we are. Pythagoras could only offer the mystical utterance, "Time is the soul of this world." Centuries later, St. Augustine famously wrote, "What then is time? I know well enough what it is, provided that nobody asks me, but if I am asked what it is and try to explain, I am baffled. Even to our most fundamental perceptions, it's slippery. We divide it into past, present, and future, but even that is fraught with difficulty." One of those early pulp writers had a mad scientist deliver a fascinating lecture on the present. He gets his victim to agree that the past no longer exists and the future does not yet exist. Then he springs his trap. The present is the moment of transition of a phenomenon from one non-existence to another non-existence. But that short moment we term the present is after all fictional in character. It cannot be measured. We can never seize it. That which we did seize is always the past. So, neither past, present, nor future exists. The victim rejects this as absurd, to which the scientist replies, "Of course." And that proves the falsity of the popular conceptions of the divisions of time. Is time smooth and continuous, like a flowing river? Or does it pass in discrete jumps, tiny indivisible ticks of a cosmic clock? Is there a time quantum, a shortest possible duration greater than zero? This question lies at the heart of modern physics, in the quest for a theory of quantum gravity, the union of Einstein's relativity and quantum mechanics. And it has profound implications for the possibility of time machines. Much of the controversy hinges on what happens when a time machine tries to form. The stresses on space-time can grow towards infinity, but quantum mechanics suggests there might be a cutoff, a point where those stresses are confined to a time interval shorter than the minimum possible tick of time. If something cannot happen in less than the minimum possible time, then perhaps it cannot happen at all. The debate rages. But what's fascinating is that this debate is almost entirely about travel to the past. Time travel to the future, you see, is not really in question among physicists. As 2 critics of past time travel wrote, after 1900, special relativity made scientific discussion of time machines possible. It was Albert Einstein in the year 1905 who shattered our old, comfortable notions of time. His special theory of relativity contains a prediction that was a stupendous shock to the scientists of his day, who were steeped in the tradition of Isaac Newton. Newton, in his masterpiece The Principia in 1687, had declared absolute, true, and mathematical time of itself and from its own nature flows equably without relation to anything external. It was a universal clock, ticking at the same rate for everyone, everywhere. Einstein, in effect, said that Newton was mistaken. There is no universal clock. Time is relative. How did he arrive at this revolutionary conclusion? Imagine two observers. One is stationary, let's say here on Earth. The other is in a spaceship, moving at a constant speed, very, very fast. Both have clocks, perfectly synchronized at the moment the spaceship departs. Now, a cornerstone of physics, a principle that goes back to Galileo, is that the laws of physics should be the same for both observers. An experiment performed on the spaceship should yield the same results as one performed on Earth. But in the 19th century, James Clerk Maxwell developed his beautiful equations of electromagnetism, which described light as a wave. And a problem arose. According to the old physics, Maxwell's equations would look different to the observer on the spaceship. This implied you could detect your own motion through space just by doing electromagnetic experiments, which contradicted the principle of relativity. The famous Michelson-Morley experiment of 1887 tried to do just that, to detect the Earth's motion through a supposed ether that filled all of space. It failed. There was no detectable motion. Einstein's genius was to take the principle of relativity as absolute. All the laws of physics, including Maxwell's, must be the same for everyone. This had a profound consequence. If the laws of electromagnetism are the same, it means the speed of light in a vacuum must be the same for all observers, no matter how fast they are moving. This is completely counterintuitive. If I'm in a car driving at 50 miles per hour and I throw a ball forward at 20 miles per hour, someone standing on the side of the road will perceive the ball traveling at 70 miles per hour. But if I turn on a torch, both I and the person on the side of the road will measure the speed of the light from that torch as being exactly the same, about 186,000 miles per second. To make this true, something has to give, and that something is time. The mathematics that falls out of this single powerful idea, the constancy of the speed of light, is called the Lorentz transformation. And tucked away inside these equations is a startling prediction: moving clocks run slow. For the astronaut in the fast-moving spaceship, time itself passes more slowly than it does for the observer back on Earth. This effect is called time dilation. At the speeds we experience in our everyday lives, it is utterly negligible. But as you approach the speed of light, it becomes dramatic. A clock traveling on a rocket ship at 99.99% of the speed of light would register the passage of 1 year. But back on Earth, nearly 71 years would have passed. The astronaut has traveled 70 years into Earth's future. For a particle of light, a photon, traveling from a star 100 light-years away, the journey takes 100 years according to our clocks. But for the photon itself, no time passes at all. Its journey is instantaneous. From its perspective, it arrives at the very instant it departs. At the speed of light, time stands still. So, special relativity gives us a ticket to the future, a remarkable scientifically sound method of time travel. But it's a one-way ticket. To get back, to undo the separation, we need something more. We need to venture into a realm where space-time itself is no longer a rigid stage, but a dynamic, flexible fabric. Is there a map for such a journey? To find that map, we need to turn to Einstein's other great theory, a way to turn that one-way ticket to the future into a return journey. Until 1949, the answer was a resounding no. But then, everything changed. And it changed because of Einstein's general theory of relativity, published in 1916. This is his theory of gravity, and it paints a picture of the universe that is radically different from Newton's. For Newton, gravity was a mysterious force, an invisible rope pulling objects towards each other across empty space. Einstein's insight was that there is no force. What we perceive as gravity is the curvature of spacetime itself. Imagine a flat, stretched rubber sheet. That's spacetime without any matter. Now place a heavy bowling ball in the middle. The sheet curves, it sags under the weight. That's what massive objects like the sun do to spacetime. Now, roll a small marble near the bowling ball. It doesn't travel in a straight line. It follows the curve in the rubber sheet, spiraling in towards the bowling ball. It appears to be attracted to it, but it's simply following the straightest possible path through a curved space. That, in essence, is gravity. As the great physicist John Wheeler so elegantly put it, space-time tells matter how to move. Matter tells space-time how to curve. This idea of a unified four-dimensional space-time was actually first articulated by one of Einstein's former mathematics teachers, Hermann Minkowski, in 1908. He delivered a famous lecture where he declared, "Gentlemen, the views of space and time which I wish to lay before you are radical. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." He envisioned the history of any particle, any object, even a person, as a line tracing its path through this four-dimensional world. He called it a world line. The entire universe, he said, is a vast, intricate tapestry of these interwoven world lines. Now, in the flat space-time of special relativity, these world lines are constrained. To get from one point in space-time to another, say from your birth to this present moment, your world line must always point towards the future. You can't go faster than light, which means your world line can never tilt over too far. We can visualize this with a concept called a light cone. Imagine a single event, the here-now. From this point, all your possible futures lie within a cone stretching upwards. All your possible pasts lie within a cone stretching downwards. The boundaries of this cone are defined by the path of light. Anything outside this cone is the LC when. Regions of spacetime you cannot reach without exceeding the speed of light, but this is all in flat spacetime. In 1949, the brilliant and eccentric logician Kurt Gödel, a close friend of Einstein's at Princeton, was playing with the equations of general relativity, and he found a solution that described a very peculiar kind of universe, a universe that was rotating. And within this rotating universe, the intense curvature of spacetime, the twisting of reality caused by the cosmic spin, did something extraordinary to the light cones. It tipped them over. Imagine the light cones all along your world line. In a normal, non-rotating universe, they all point in the same direction, upwards, towards the future. But in Gödel's universe, as you travel, the cones gradually tilt. And if you travel far enough, on a wide enough path, the future part of your light cone can tilt over so much that it begins to overlap with the past part of the light cone back where you started. This means you can plot a path, a world line, that always moves into your local future. Your watch always ticks forward. You continue to form new memories. But that eventually loops around and brings you back to a point in space-time that is in your own past. You would arrive before you departed. Gödel had discovered what physicists call a closed time-like curve. He had discovered a time machine written into the very mathematics of reality. Now, our universe doesn't appear to be rotating like Gödel's. Observations suggest that if it is spinning at all, it's doing so far too slowly to create these effects. Gödel's solution also required a non-zero cosmological constant, a sort of cosmic anti-gravity that Einstein had initially put into his equations to keep the universe static, a decision he later called his biggest blunder. But the door had been opened. Gödel had shown that general relativity did not forbid travel to the past. It was no longer a logical impossibility. It was now a question of engineering. Could we, perhaps, create these conditions locally? Could we warp space-time enough to bend a world line back on itself? Gödel had unlocked a door in the architecture of reality. He had shown that a pathway to the past was not forbidden by the mathematics of the universe. But what lies on the other side of that door? If you could step through it, what would you find? And more importantly, what could you do? The idea of a world line bending back has a fascinating parallel in quantum physics. In the 1940s, the physicist Richard Feynman suggested that an antiparticle, like a positron, could be interpreted as its regular particle counterpart, an electron, traveling backwards in time. Imagine a gamma ray spontaneously creating an electron-positron pair. They fly apart. Later, the positron meets another electron, and they annihilate in another flash of energy. That's one way to describe it. But Feynman offered another. He said we could think of it as the world line of a single electron. It travels forward in time, then it encounters an energy burst which is so powerful it causes the electron to recoil, not just in space, but backwards in time. It travels into the past for a short while, appearing to us as a positron, before another interaction causes it to recoil forward in time again. It's as if a pilot flying low over a road suddenly perceives three roads, and it's only when two of them merge and disappear that he realizes he has simply passed over a long switchback in a single road. So the idea of world lines bending and looping is not just a mathematical curiosity of general relativity. It has echoes in the quantum world too, and it highlights a critical point about any potential time machine. It must move through space as well as time. HGG. Wells's classic machine, which remained stationary in his laboratory as the centuries flashed by, has a fatal flaw. If it travels through time, rather than jumping over it, then at the very micro-instant after the lever is pulled to go into the past, the machine will collide with itself a micro-instant before the lever was pulled. It would occupy the same space at the same time as its earlier self. The result would be a catastrophic release of energy, a nuclear detonation. And there's the paradox. If the explosion happens before the lever is pulled, how was it ever pulled in the first place? Real-time machines, the kind allowed by general relativity, must be space-time machines. They must navigate a path through the four-dimensional cosmos. But if such paths exist, if we could build such a machine, what does that mean for our place in the universe? Does it mean the past is a landscape we can visit? And if so, is it a landscape we can change? The notion that we exist in more than just three dimensions can be unsettling. Einstein himself wrote, "The non-mathematician is seized by a mysterious shuddering when he hears of four-dimensional things, by a feeling not unlike that awakened by thoughts of the occult." And he was right. How could there be four spatial dimensions? We perceive three, and that, it seems, is that. But for physicists and for storytellers, this idea of hyperspace is a powerful tool for thinking about the universe. Our four-dimensional spacetime could, mathematically, be thought of as just the surface of a higher-dimensional, five-dimensional world. Think of the inhabitants of a two-dimensional world like the characters in the classic book Flatland. They live on a flat plane and have no concept of up or down. For them, our three-dimensional space is their hyperspace. If you were to pass your finger through their world, they wouldn't perceive a finger. They would first perceive a point appear from nowhere, which would then expand into a circle, then change shape, shrink back to a point, and vanish. They would interpret this sequence of events happening over time. But for you, the three-dimensional being, it's just one solid object, your finger, existing all at once. This is the analogy for our own universe. Perhaps our entire four-dimensional space-time, from the Big Bang to the distant future, exists all at once as a single object in a five-dimensional hyperspace. And our perception of the flow of time is simply our consciousness moving along our world line through this already existing structure. This concept leads to the idea of wormholes. If you want to travel from one point on the surface of an apple to the opposite side, you can crawl all the way around the skin, or a worm could chew a tunnel straight through the middle. That tunnel is a shortcut through the apple's hyperspace, its three-dimensional interior. In the same way, a wormhole could be a tunnel, a shortcut through five-dimensional hyperspace, connecting two distant points in our four-dimensional spacetime. It's an idea that science fiction has used for decades to explain faster-than-light travel. Instead of spending thousands of years traversing the vast distances of normal space between stars, you could just pop through a wormhole and arrive almost instantaneously. The journey through hyperspace is shorter, but as we'll see, these shortcuts through space can, with a little bit of Einsteinian ingenuity, be turned into pathways through time. The idea of time itself being the fourth dimension, rather than an additional spatial one, is the prevailing view in physics today. And it's an old idea. The French mathematician Jean Laurent d'Alembert wrote in 1751 that a clever acquaintance of mine believes that duration could be regarded as a fourth dimension. But it was H.G. Wells with The Time Machine who seared this concept into the popular imagination. His time traveler explains to his dinner guests that there is no difference between time and the three dimensions of space, except that our consciousness moves along it. He holds up a series of portraits of a man at different ages, 8, 15, 23. All these, he says, are evidently sections of his four-dimensional being, which is a fixed and unalterable thing. This vision of reality, where the past, present, and future all exist simultaneously, is known as the block universe. It's a staggering thought. It implies that the dinosaurs are not gone, they are just in a different part of space-time. The future is not unwritten, it's already there, waiting for our consciousness to arrive. Einstein, in a letter of condolence to the family of his lifelong friend Michele Besso, wrote, "Now he has preceded me briefly in bidding farewell to this strange world. This signifies nothing. For us believing physicists, the distinction between past, present, and future is only an illusion, however stubborn a one." If the universe is such a block, a four-dimensional structure existing in its entirety, then time doesn't really flow. It just is. The physicist Hermann Weyl described it beautifully. The objective world simply is, it does not happen. Only to the gaze of my consciousness, crawling upward along the lifeline of my body, does a section of this world come to life as a fleeting image in space which continuously changes in time. This seems to be a picture of a fatalistic universe. A universe where free will is an illusion. If the future is already there, then all our choices have already been made. Our struggles, our decisions, our triumphs are just us playing out a pre-written script. It's a deeply unsettling idea for many, and it's why the concept of the block universe is so philosophically charged. It forces us to confront the deepest questions about our own agency. Are we the authors of our lives, or are we just readers, turning the pages of a book that has already been written? This is the block universe, a static, four-dimensional sculpture in which all of history is frozen. It's a majestic, if somewhat chilling, vision. But does it truly capture the full nature of reality? Or is there a deeper, more chaotic layer to the cosmos, a place where the neat lines of space-time begin to fray and the singular story of the universe shatters into an infinity of possibilities? If time is a dimension, does it have a direction? Our experience certainly suggests it does. We remember the past, but not the future. A broken egg never spontaneously reassembles itself. Heat flows from a hot cup of coffee into the cooler air, never the other way around. This apparent one-way nature of time is what physicists call the arrow of times. And the most powerful explanation for it comes from a concept called entropy. Entropy is, in simple terms, a measure of disorder or randomness. The second law of thermodynamics, one of the most fundamental laws in all of physics, states that the entropy of a closed system will always tend to increase over time. Think of a new deck of cards, perfectly ordered by suit and number. That's a low entropy state. Now shuffle it. The cards become randomized, disordered. That's a high entropy state, and you can shuffle it for the rest of your life, but it's astronomically unlikely that you'll ever shuffle it back into its original, perfect order. The universe as a whole seems to behave this way. It started in a highly ordered, low entropy state at the Big Bang, and it has been getting more disordered ever since. This relentless increase in entropy gives time its direction. The past is the direction of low entropy, the future is the direction of high entropy. The arrow of time is, in essence, the arrow of increasing disorder. But there's a puzzle here. All the fundamental laws of physics that govern the interactions of individual particles work just as well forwards in time as they do backwards. There's no inherent directionality in them. So why does the macroscopic world we experience have such a powerful arrow of time? This is one of the deepest mysteries in physics, and it's led to some fascinating speculations. What if there are regions of the universe where entropy is decreasing? where time, for the inhabitants of that region, runs backwards relative to ours. They would experience their world completely consistently. They would remember their future and be born at the moment of their death. It's a mind-bending idea, but one that is not explicitly forbidden by the laws of physics. So, if we accept this block universe, this four-dimensional reality where past and future are fixed, what does that mean for our time traveler who wants to go back and interfere with his grandfather? The modern view, the one dictated by the principle of self-consistency, is that he simply can't change the past. Why? Because the past he is traveling to is the one and only past that ever existed, and it's the past that already includes his visit. He cannot change what happened, because what happened is the story of him being there. This doesn't mean he's an ineffectual ghost. He can absolutely affect the past. A careless time traveler could be the one who starts the Great Fire of London. He could be the one who gives Isaac Newton the inspiration for the law of gravity. But he cannot do anything that would create a logical contradiction. He cannot kill his grandfather because, if he had, he wouldn't exist to make the journey. So, what stops him? He's there, with the weapon in his hand. What mysterious force intervenes? The answer is nothing. There is no force. The situation is simply not a possible one. In a self-consistent universe, the chain of events that would lead to him successfully pulling the trigger simply does not occur. The gun might jam, he might slip, a bird might fly in front of him at the crucial moment. The universe doesn't conspire to stop him. The consistent history of the universe is simply one in which he fails. It is as logically impossible as drawing a square circle. Free will, in this context, is simply the freedom to try, but success is not guaranteed. But this leads to an even deeper, more mysterious kind of paradox, one that doesn't involve contradictions, but rather uncaused causes, the causal loop. Imagine a mathematician who has struggled his whole life with a famous unsolved theorem. One day, an old man appears, a time traveler, who gives him the completed proof. The mathematician publishes it and becomes famous. Years later, as an old man, he builds a time machine, travels back, and gives the proof to his younger self. So, who actually came up with the proof? It seems to have appeared from nowhere, an idea existing in a self-contained loop with no point of origin. This is not a contradiction. It is perfectly self-consistent, but it is profoundly mysterious. It's an information paradox, or consider the sexual paradoxes, a favorite of science fiction writers. Robert Heinlein wrote what is often considered the definitive story on this, a tale so convoluted that it's almost impossible to summarize, involving a character who is, through a series of time travel events, their own mother, father, son, and daughter. The world line of this character is a completely self-contained loop. Again, there's no logical contradiction, but it challenges our deepest intuitions about origin and identity. So, while the grandfather paradox might be a red herring, these causal loops suggest that if time travel is possible, the universe might be a place of profound and beautiful mystery, where information and even people can exist without a conventional beginning. It's a universe that is not just a story, but perhaps a collection of stories, some of which are written in a circle. So, the universe seems to have a built-in protection against logical contradictions, a principle of self-consistency that keeps history coherent. But what are the physical tools it might use? If we could really build a time machine, what would it look like? Is it a spinning cylinder of impossible density? Or perhaps a tunnel bored through the very fabric of reality itself? If physics allows it, how might we actually build one of these machines? On paper, physicists have already invented several. They all require mind-boggling amounts of matter or energy, and often in forms that we call exotics, which is a polite way of saying we have no idea if it can even exist. One of the earliest ideas involved black holes. A rotating black hole, known as a Kerr hole, doesn't have a single point of infinite density at its center like a non-rotating one. Instead, its singularity is smeared out into a ring. And the mathematics of general relativity suggests that if you could pass through that ring, you might emerge not just in another place, but in another time, or even another universe. The problem is, the tidal forces near a black hole would tear any conceivable spaceship, or human, apart. So, probably not a practical method. Then, in 1974, the physicist Frank Tipler published a paper describing a different kind of time machine. It was an infinitely long, incredibly dense cylinder, spinning at nearly half the speed of light. The immense rotation would drag space-time around with it, tipping the light cone so severely that closed time-like curves would form around the cylinder. By flying a spaceship in a spiral path around it, you could travel into the past. But there are problems. It has to be infinitely long. And the material it's made of would have to be trillions upon trillions of times denser than the nucleus of an atom and strong enough to withstand centrifugal forces that would tear any normal matter apart. So, again, perhaps not something we'll be building next week. A more recent and perhaps more plausible idea involves cosmic strings. These are hypothetical, incredibly thin, and unbelievably massive threads of energy left over from the Big Bang. In 1991, the physicist J.J. Richard Gott showed that if two of these strings were to fly past each other at nearly the speed of light, the space-time around them would become so warped that it would create a region where time travel to the past is possible. But the most promising candidate for a time machine, the one that has captured the imagination of physicists and storytellers alike, is the wormhole. As we've discussed, a wormhole is a theoretical tunnel through space-time. For decades, it was thought they would be unstable, pinching off and collapsing faster than even light could travel through them. But in 1988, a group of physicists at Caltech, led by Kip Thorne, showed that a wormhole could theoretically be held open. You would need to thread it with a type of exotic matters that has negative energy density. In other words, matter that has a kind of gravitational repulsion. It would push the walls of the wormhole apart, stabilizing it. We don't know if such matter can exist on a large scale, but it's not forbidden by quantum mechanics. So, let's assume an advanced civilization has found or created a stable, traversable wormhole. How do you turn this shortcut through space into a gateway through time? This is where special relativity comes back into the picture. You take one mouth of the wormhole, let's call it mouth B, and you put it on a spaceship. You then fly it on a long, high-speed journey, just like our astronaut twin, while mouth A stays put. When mouth B returns because of time dilation, less time will have passed for it than for mouth A. Let's say 10 years have passed for mouth A, but only 1 year has passed for mouth B. The wormhole now connects 2 points in space, but it also connects 2 different times. It connects a point in time, say the year 2010, at mouth A, with a point in time 9 years earlier, the year 2001, at mouth B. If you walk into mouth A, you will emerge from mouth B 9 years in the past. You have a time machine. This is, by far, the most theoretically sound model for a time machine that we have. But it's not without its challenges. There are concerns that as soon as you create such a time loop, virtual particles and radiation could circulate through the wormhole, getting amplified with each pass, until their energy becomes so immense that it destroys the wormhole in a feedback loop. This is what Stephen Hawking believes. He has proposed what he calls the chronology protection conjecture, which essentially states that the laws of physics conspire to prevent time travel to the past on a macroscopic scale. We seem to have a recipe then. A blueprint for a time machine sketched out in the language of general relativity. But there is a ghost in this machine, a potential flaw so catastrophic it might ensure that no such device could ever be switched on. What happens when the universe itself fights back? Stephen Hawking argues that the best evidence we have that time travel is impossible is that we haven't been invaded by hordes of tourists from the future. But there's a neat answer to that, an answer that is consistent with all the models we've discussed. You cannot use a wormhole, or a Tipler cylinder, or cosmic strings to travel back to a time before the machine itself was created. You can only travel back to the moment of its activation. So, if we build the first time machine tomorrow, tourists from the future could start arriving the day after tomorrow. But they could never visit the dinosaurs or see the construction of the pyramids because no time machine existed back then to take them there. This neatly explains the absence of future tourists. The party hasn't started yet. But what if there's another way? a way that sidesteps all these paradoxes of a single, consistent timeline. This brings us to the edge of known physics, to the strange and wonderful world of quantum mechanics. As we've seen, general relativity describes a smooth, curved space-time, but quantum mechanics tells us that on the very smallest scales, the universe is a jittery, probabilistic, uncertain place. The two theories are currently incompatible. The quest for a unified theory of quantum gravity is the holy grail of modern physics. And within this quest, there are ideas that completely reframe the problem of time travel. One of the most radical is the many worlds interpretation of quantum mechanics. It suggests that every time a quantum event has more than one possible outcome, the universe itself splits into multiple copies, one for each outcome. In one universe, the particle went left. In another, identical universe, it went right. This splitting happens constantly, creating a near-infinite tree of parallel realities. If this is true, it provides a perfect solution to the grandfather paradox. If you travel back in time and kill your grandfather, you don't erase yourself from existence. You simply cause the timeline to split. You create a new branch of reality, a new universe, in which you were never born. But you, the time traveler, would still exist, now stranded in this alternate history you've created. Your own original timeline, the one you came from, remains completely unchanged and unaffected. There is no paradox because you haven't changed your past. You've created a new one. This is a breathtakingly extravagant idea, an infinity of universes branching every instant. But it's a logically consistent way of resolving the paradoxes that have troubled thinkers for a century. It replaces the block universe's rigid fatalism with an endless vista of possibilities. Every choice we make, every quantum fluctuation, creates new worlds. So where does this leave us? We stand at a fascinating crossroads. On one hand, we have Einstein's general relativity, a classical theory that paints a picture of a block universe where the past, present, and future are all laid out, and time travel to the past seems possible, but only in a way that is self-consistent. You can be a part of history, but you cannot change it. On the other hand, we have the tantalizing hints from quantum mechanics, which suggest a universe of infinite possibilities, a branching tree of realities where the past is not a single, immutable country, but a gateway to countless others. The final answer, if there is one, will likely lie in that undiscovered country of quantum gravity. It may be that Hawking is right, and that some deep principle of nature prevents the past from ever being visited. Or it may be that the universe is far more accommodating, allowing for these strange loops and pathways through its four-dimensional fabric. For me, the journey into these ideas is as profound as any physical journey to the stars. It forces us to question the very nature of our reality, the meaning of now, the substance of memory, and the shape of the future. The possibility of time travel isn't just a question of physics and technology. It's a reflection of our own deep yearning to understand our place in the cosmic story, a story that is written not just in 3 dimensions of space, but in the mysterious, beautiful, and perhaps navigable 4th dimension of time.